Hello guys on YouTube. In this video tutorial, we are going to consider the proof of the derivative of exponential function e to the x. So before we begin proving out the derivative, let's state what the derivative is. It says that if y is equal to e to the power of x, then the derivative dy dx is simply equal to the same e to the power of x. So like we said at the beginning of this video, the purpose of this video is to show you why this is true. So we'll be considering using the definition of derivative. So from the definition of derivative, we have that for any function, then the derivative of that function, dy dx, which is the same as f prime of x, is simply equal to the limit as h approaches 0, where h is just an increment in the x-axis. Okay, where some textbooks usually used to represent it as delta x. So regardless, just know that that's what h means next sense. So we have of f of x plus h minus f of x all divided by h. So that's what the definition of derivative says, and that's what we're using to show that the derivative of e to the x is still the same as e to the x. Perfect. So now, if y is equal to f of x, we know that by definition, we know that y is equal to f of x, which is the same thing as e to the power of x in this case. What do you think would be the value of f of x plus h? Because we need that to substitute right into the definition of derivative. Well, what f of x basically means next sense is that wherever you see x in f of x, kindly replace with x plus h. So since this is the only place we have x in f of x, it means f of x plus h will simply be equal to e to the power of x plus h. And here we go. We can now proceed on substituting. So this clearly means that the y dx would now be equal to the limit as h goes to 0 of f of x plus h, that's e to the power of x plus h, then minus f of x, that's e to the power of x, then we have to be divided by h. Excellent. So simplifying forward, we can try to apply our knowledge in indices to this first term right here. In what manner? Let's see. So now we have the limit as h goes to 0 of e to the power of x plus h can actually be re-expressed as e to the power of x multiplied by e to the power of h. I would like to clarify that for those who might be wondering how. In indices, you agree that a to the power of x multiplied by a to the power of y is equal to a to the power of x plus y. Now, one thing about the law of indices is that if this is what you are having, you can actually turn it to this. And if this is what you are having, knows that it is equal to this. Okay? Perfect. Now, if that is the case, what do you think would be e to the power of x times e to the power of h? Well, notice that will end up giving us this. So therefore, expressing e to the power of x plus h as this is still perfect. We are still doing math. Are we together? Perfect. So therefore, we now have minus e to the power of h divided by h. Now, what do you think could be our next step? Well, this should be x and not h. Our next step could be such that we can factor out a common factor, as we have e to the power of x at both sides of the numerator expression. So this clearly means that the y dx will now be equal to the limit as h goes to 0 of e to the power of x multiplied by e to the power of h minus 1 divided by h. Am I communicating? Perfect. Now, this is a limit that is with respect to h. However, this is a function that is with respect to x. Since the limit and the function doesn't correspond, it means they have no business, and so therefore we can take e to the power of x outside the limits, and then we can have e to the power of x multiplied by the limit as h goes to 0 of e to the power of h minus 1 divided by h. Excellent. So now at this point, we want to do some manipulation. So let's consider e to the power of h minus 1 to be equal to some number k or n. To make things easy, let's use n. So if e to the power of h minus 1 is equal to n, what will be the value of h? Well, we can isolate h by in the first place, adding 1 to both sides. So adding 1 to both sides, we have e to the power of h. Let me put implies that e to the power of h minus 1 plus 1 would be equal to n plus 1. And these cancels out, and we have e to the power of h to be equal to n plus 1. So while I get rid of some of these stuffs to have enough space, we're thinking about what would be our next step in order to isolate h. So we can get rid of this. So did you guess right? Let me know in the comment section below. Our next step would be such that we can take the natural log of both sides so that h can come to the front. So taking the natural log of both sides, we have ln e to the power of h to be equal to ln n plus 1. Perfect. Now, ln is a log with a base of e. So we have log of base e to e to the power of h to be equal to ln n plus 1. I don't really want to change this one to log of base e because it's not necessary. Am I communicating? Perfect. There's something I want to show you here, and that's the reason why I have to turn the ln to log of base e. Now, one of the laws in logarithm is that when you have the log of a certain base with respect to an argument such that the argument is having an index, then the index of the argument can actually come to the front of the log. Am I communicating? So this h can come all the way to this point, and then we have h multiplied by the log of base e to be equal to ln n plus 1. Am I communicating? Perfect. So now we have this. Well, don't forget, we actually stopped at the y dx to be equal to the limit as h goes to 0 of e to the power of h minus 1 divided by h, though we still have e to the power of x outside there. So this is where we stopped before we begin manipulating. So it means we are still going to come back here. Is that okay? Excuse me. So put that back in mind. Now, similarly, in logarithm, we learned that the log of certain base with respect to the same thing is simply 1. So it means log of base e to e is simply 1, and 1 times h is h. And finally, we got our value of h to be ln n plus 1. Am I communicating? Perfect. So now, having gotten the value of h, the next thing we want to consider doing is to observe the behavior of n as h approaches 0, because we want to turn all the entire parameters right here into n. We want to turn them, excuse me, we want to express them in terms of n. Sorry about that. So as I was saying, we basically want to express all the terms, all the parameters in the limit. We want to express them in terms of h. So, sorry, in terms of n. So basically, we need the behavior of n as h goes to 0. So to do that, we can consider using what we said earlier. We said that earlier, e to the power of h minus 1 is equal to n. So what will happen to n as h goes to 0, let's say? Well, notice that as h goes to 0, e to the power of h will be approaching 1. Because anything goes to the power of 0 will be 1. And by the time we minus 1 from the result, we'll be having a value that is very, very closer and closer to 0. So this clearly means that as h goes to 0, n would also be going towards 0. And with all this, we are good to go on actually changing the parameters. And this clearly means that y dx will now be equal to e to the power of x multiplied by the limit. Now instead of h, we now want to consider n approaching 0 of e to the power of h minus 1. We said that's entirely n. So we have n divided by h is simply the natural log of n plus 1. So that's ln n plus 1. Am I communicating? Perfect. So now, let me actually get rid of this one as they have no use anymore. So let me write one more step here, or even if possible 2 more. So now what should we do next? Well, let's try to take the reciprocal of this fraction. So taking the reciprocal of this fraction, we have the y dx to be equal to e to the power of x, then multiplied by the limit as n approaches 0 of 1 divided by n divided by ln n plus 1. Perfect. Now, why do we need to change the reciprocal? Why do we need to reciprocate this function, this fraction? Why do we need to reciprocate it? Also, taking the reciprocal of the function actually changes the structure. So it means this entire stuff right here is different from what we are having above. So we need to make things equal. And to make it equal, basically, all we need to do is to flip the position of these two fractions. And so therefore, we now have the y dx to be equal to e to the power of x multiplied by the limit as h goes to 0 of, I use h again, as n goes to 0 of 1 divided by, so that be ln n plus 1 divided by n. So this is how it should be in order to make it the same as what we have right here. Is that okay? Perfect. Now if you evaluate this, you will end up having this right here, which makes sense. So now let's re-express this fraction. Is that okay? So if we re-express this fraction, we have the y dx to be equal to e to the power of x multiplied by the limit as n goes to 0 of 1 over n ln n plus 1, and we still have this one on top. So basically, this 1 over n can act as an index to this natural log. And so therefore, we have e to the power of x multiplied by the limit as n goes to 0 of 1 divided by ln n plus 1 all to the power of 1 over n. Perfect. And again, we are out of space. Let's get rid of this one. So having done that, let's basically distribute the limits to the entire fraction. So therefore, we now have our dy dx to be equal to e to the power of x multiplied by the limit as n goes to 0 of 1 divided by the limit as n goes to 0 of ln n plus 1 to the power of 1 over n. Perfect. Now this is a limit that is with respect to n, and the function is just a constant function, and the limit of a constant is simply a constant. So according to the properties of limits, this clearly means that the y dx and with the y dy. The y dx is simply equal to e to the power of x multiplied by 1 divided by the limit as n goes to 0 of ln n plus 1 to the power of 1 over n. Okay, just bear that with me. Let me get rid of this one so we can have enough space. Perfect. So now, on to the next step, we have the y dx to be equal to e to the power of x multiplied by 1 divided by. Now this is the limit of a continuous function, because natural log is a continuous function. It clearly means that the limit can actually come into this function. Okay, and so therefore we can express it as limit as n goes to 0 of n plus 1 to the power of 1 over n, and close the bracket. Now everything we have within this big parenthesis is nothing but e. And so therefore we have e to the power of x multiplied by 1 divided by ln e. And ln e, don't forget, is simply 1. We said that earlier. And finally we have e to the power of x times 1, which is still e to the power of x. And this is how the derivative of e to the power of x is gotten to be e to the power of x. So for those who might be wondering how this is e, so I would suggest you plug in a value that is closer and closer to 0 into this entire expression, and you will observe that at the end of the day you're getting a result like 2.71828. Then you keep on getting values continuously, okay, or randomly. So that value is what we call e, the Euler's number.